Welcome back again. This little lesson is going to be looking at how we deal with forces on an incline. An incline, or a hill, another word for incline, a slope, a grade, whatever you want to call it. Forces on an incline, and how that changes our understanding of a situation. So let's begin by doing a quick summary of what we've seen so far. We have seen that if we have a mass sitting on a level surface, there are a number of different forces that will occur. We know that there is the force of gravity pulling down on an object, so we label it Fg. And we know that Newton's laws tell us that there will be a force of the ground pushing back up called the normal force. We also know that if you try to pull this block horizontally, let's say, I'm going to pull it this way just for fun. Let's say we pull it this way, there would be an applied force that you are applying to the block. And we've also learned, because it's on the surface, that there will be a friction force that tries to oppose the motion of the block. And so we've seen pictures that look something like this. Simple cases of sliding things across floors. What would happen, though, if the whole thing took place on a slope? Let's say we had a slope here, and there was some angle to the slope. We'll call it angle theta. Let's put our mass here on the slope. And let's try and draw the arrows. Now you might be tempted to draw your force of gravity this way because of the way you drew it before. But that doesn't make sense, because think about the way gravity works. It always acts downward. Gravity always pulls straight down towards the Earth. So the gravity force would have to be drawn straight down this way, not the other way. And then you might think, okay, well then maybe I'll draw my normal force up here like this, because you're so used to drawing it opposite to gravity. But that won't work either, because normal forces, remember the word normal means perpendicular, these forces must always act perpendicular to the surface, because the surface has to push perpendicular to itself. That's the way surfaces work. And so we would have to draw the normal force sort of perpendicular to the hill surface, and it would bend this way, right? So you can see how that's perpendicular to the surface of the hill. So right away we have a little problem here. I'm going to label this one Fg so we don't forget. Then if we go back to our horizontal forces, or the other forces that I drew in red, let's say we're trying to pull this block up a hill. We would have to pull this way, which would be in line with the hill. And if we were pulling it up the hill and the block was sliding upwards, then the friction force is going to try to stop us and work this way. So this is what our picture would look like. Everything seems to get bent over except the gravity. The gravity force remains the same. That's why I drew it in blue, so that it would stand out. Now, under normal circumstances, if we consider our regular xy axis like this, we would see that only the force of gravity is lined up with the y-axis, which means we would have to find all the components of all the other forces. And that's a lot of work. So what we can do as a little bit of a trick is we can rotate our axis so that it matches the hill, so that the x-axis turns into the hill and the y-axis now becomes perpendicular to the hill. So if we do that, let me just kind of sketch here what the new axis would be. It would look like this. There's our new xy axis. And when we rotate it like this, the three forces that were off axis, the F applied, the FF, and the Fn, are now nice and conveniently on axis. And only the gravity is the one that's odd, which means we only have to resolve the gravity into its components by tilting our axis this way. Of course, we just have to remember we're working with a tilted axis, and every time we say x now, we mean up and down the hill. And every time we say y, we now mean perpendicular to the hill. So it's not quite the same. Let's draw the components of the gravity force. How much is on the y-axis? Okay, got interrupted by a phone call, but we're all set. What we were trying to do here is we were trying to resolve the gravity into its, we call it the vertical component, but it's not really vertical anymore. It's the y component, right? I'll call it Fg with a little y to remind us that. Okay? And then we also have to draw in the x component on our axis. So this would be Fgx. Okay. Now what a lot of students do is they make the mistake of drawing this triangle incorrectly. I'm going to show you some of the mistakes that they make. They have a hill, and they draw the gravity force this way, which is fine. And then I see some students going like this. They draw this all the way down here, and they draw this across. Well, that doesn't make sense. That's the old x-axis, before we tilted it. The new x-axis, as you can see in the picture that I drew, the red arrow, is lined up with the hill. It's parallel to the hill. The other thing I see students doing is drawing the other one backwards or weird. Instead of drawing it straight down, they kind of draw it over this way. And then they draw a line down like this, and they get a gravity force over here. So I don't know, they do something like that. The important thing that you have to notice when you draw your picture, because these are all incorrect, is that you're drawing the components of the blue arrow that are on the x and y axis. This must be a, oh rats, I erased that. This must be a right angle between the forces. Let me put those back in. This must be a right angle right here. And the green arrow, the y component arrow, must be perpendicular to the hill. And okay, see, if I even, I don't want to draw too many things on our picture, but see here, perpendicular to the hill. And the red arrow must be parallel to the hill in order to draw this correctly. All right. So now let's look at what happens. When we do this resolving of vectors, remember what we've done. The blue arrow now disappears because we have replaced it with its two components. So we don't even need to worry about the blue arrow anymore. We've replaced blue with two pieces that add up to blue. Remember, tip to tail, see the tip to tail, the two vectors add to the blue. So that's the point. Now what we're going to do is we're going to draw our net force equations. We'll start with what we call F net y. And if I draw F net y, what I will get is I need the sum of all the y-axis arrows, which I drew in green conveniently so you could see them. So what we have is a normal force on the y-axis, and we have what's called our new FGY. Okay? You see how that's a little bit different than what we had before, right? If I quick sketch up here, the old way of writing them, looking at this picture before we started hills, F net y was equal to Fn plus Fg. But now it's Fn plus only the Fgy component. And if we look at F net x, we'll see that here it was the force applied and the force of friction that were involved. And we'll see that if we have F net x written now, we actually have an additional arrow to include. We still have the force applied and the force of friction, but now we also have this additional Fgx component. So we still have our applied force, and we still have friction, but now we have Fgx. What effectively happens is that a little bit of gravity ends up in both of the equations now. That's what's different. So some of the gravity can actually slide you down the hill in the x direction. And of course the other part of the gravity is what's pulling you into the hill, and of course that's going to be important for creating normal forces and friction. So gravity shows up twice. All right. So these are how our equations would be laid out. Now I guess what we can do is work through an example. Let's add some numbers to our picture, and let's see how it would play out. Okay? So let's do something relatively simple. We'll take a block and we'll give it an actual mass. Let's say the mass of that block is 20 kilograms. And let's say that when we do this question, I'll write it underneath here, there's going to be some friction. So the mu, the coefficient of friction, will be 0.3. And let's ask ourselves a question that we can answer. How much force is required to pull the block up the hill at a constant speed? Right? We're just going to drag this block nice and smooth at constant speed up the hill. But how much force will that take? Well, let's draw in our arrows. So the first thing we do is we draw, oh wait, before we do that, I also need to tell you an angle for the hill. So we'll make it let's make it a 40-degree hill. Nice and steep. Okay, so we draw in our gravity force. Fg. It's always down, so you can never get this wrong. It's always down. The other force that we can never get wrong is the normal force. It's always perpendicular to the hill, straight up out of the hill, 90 degrees from the hill, Fn. Now we look at if we were pulling this up the hill, obviously we must apply a force up the hill, so we're going to have an applied force here. And since we are sliding it up the hill, our friction force is going to try to oppose that motion, work against us. So there's our picture. Looks just like the one we drew before. But now we understand that the blue arrow is a little bit of a problem. So we're going to tilt our axis. We're going to tilt our XY axis so that it's now this way, right? There's our X over here. We've tilted our axis, and now we're going to resolve the gravity into its two components. There will be a component here. Remember, 90 degrees there. Remember that this is a 90-degree angle. This one we call FGX because it's parallel to the axis, which is the hill now. And we call this one FGY because it's perpendicular to the hill. Now we know how to figure those out, don't we? If we could get an angle in the triangle, we can actually figure out a lot of numbers here because we know that gravity is mg. So let's remember that gravity is mg. That means that this side, if I could figure out this little angle right here, right, I could call this FG, and it's adjacent, so actually let me call that FG, which is mg, sorry. mg times the cosine of this little angle that I've drawn. Let's see if we can figure it out. Well, if I look right here, I can imagine a triangle that's in the black and blue. I can imagine this triangle right here. I'll draw it. And I can realize that this is 90 degrees and the other angle is 40 degrees. So this has to be 50 because they have to add to 180 in the triangle. Then I can look at this and see that this is a 90-degree angle between the green and the black. And so 50 plus 40 is equal to 90. So conveniently, the angle inside the triangle works out to be the same angle that is on the hill. So that's kind of convenient. And that will always be the case if you choose to draw your components of gravity down first and then over. Okay? So get in the habit of doing that. It'll save you some frustration. Okay, so that means that the value of this green line is mg cos 40. And the value of the red line is mg sine 40 because it's opposite. Remember, mg is my hypotenuse, so mg sine 40. So now I can actually use those numbers. And we don't need the blue one anymore because we've replaced it. So let's do our F net forces. Let's start with F net y, which is green. F net y, there are two forces. There is the normal force, and there is what I called FGY. Now, if we're sliding this at a constant speed, there should be no acceleration along the hill. And obviously, we don't expect any acceleration in the direction of the green arrows on our y-axis. The block is not going to suddenly drift off the hill or go into the hill. So I can replace Fnet with ma because of Newton's second law, Fn, and I can also replace this Fg with mg cos theta, 40 degrees. Okay, now I'm going to put in as many numbers as I can, and I'm also going to tell the math about directions. Whenever I put the numbers in, that's why I like to also tell the math which way things are pointing. So, if we have a mass, it was 20 kilograms, but 0 is the A we would expect. We don't expect acceleration on this y-axis. So that leaves me with Fn. Now, mg cos theta, if you look at the picture, is pointing sort of in a downward direction, or a negative y direction. So I have to put a negative sign on here. When I start crunching it out, the mass is 20, g is 9.8, and I have my cos 40. So now I can crunch all that out and get an actual number that I can get for that. So 20 times 9.8 is 196, and if you multiply that by the cosine of 40, you get about 150-ish. I'm going to round it off to no decimals. So it becomes this, and now we can see that if you move it to the other side, my normal force is 150 newtons. That's a little bit less than the weight of the object now. The object weighs 196, but not all of that 196 is pulling down into the slope. Some of it is being used to pull down the slope, right? So that's why it's a little bit different number. The normal is no longer just equal to the weight of the object. That's a very important thing. A lot of students will forget that, and they'll just do Fn equals mg, because that's how it was way back when we did the original kind of pictures where everything was flat. I'll go back to that picture, right? We said that Fn is just equal to Fg when you did your equations. And that's no longer the case. So you have to be careful not to make that mistake. Okay, so now that I have my normal force, now I can continue on, and we're going to have to jump around a bit, and we'll do our Fnet x, which I had color-coded in red there, Fnet x. And if we go back to the picture, if you look at the picture, there are 3 red arrows I need to include. There's an F applied, an SF, and this new FGX, which has come out of the gravity. So let's put them in. There's an F applied, there's an FF, force of friction, and our new FGX. All right? Good. Now, let's go through the process. Newton's law, MA, F applied, something that we're looking for. This is going to be mu Fn. Remember, mu Fn for friction. And FGX is going to be, we said, mg times the sine of the angle, which happens to be 40 in this case. Let's put in some numbers. 20 for the mass, but if you recall, the question said we're going to slide this up at a constant speed. So even on the x direction, we're not accelerating, so we get a nice 0 there. F applied is the answer to the question that we're searching for. Let's go look at our friction arrow. Here's where the friction arrow is. It's mu Fn, but it's also pointing to the right on the x-axis, the bent x-axis. So it's a positive value for friction. So when I put in the mu, which I believe I said was 0.3, we better go back and check on that. There it is, 0.3. And the Fn, which I calculated as 150 up here, now I put that in, and I leave it as a positive number because it is going to the right on my x-axis. You must look at all your arrows and figure out which way they're pointing. Now here's the interesting thing. When I get to this next part, look at the arrow for gravity. Here it is. I'm going to redraw it there. There it is in purple, right there. Look at the direction it's pointing. It is pointing in the positive x direction. So it's actually a positive number. And it's weird because we've always used gravity as a negative number up till now. Now, only part of the gravity is negative. The y part, there it is there, See how it's negative, the y part of the gravity, FGY. But the x part happens to be a positive number because it's pointing in a positive x direction. So I leave it positive, and I put in all the numbers that I need, and I put in the sine of 40 degrees. So it is possible for gravity, at least in part, to have a positive direction, depending on how you set up your question. Okay, so now we can work this out, and you can see what's happened. Everything's disappeared except for the F applied, which is what I want to find out. The beautiful thing about net force equations is that the answer will always appear. It doesn't matter what you're looking for, it's in here somewhere. So we don't have to worry about trying to figure out what the answer would be. 0.3 times 150 is going to give us about 45, and 196 times the sine of 40 is going to give us about 126 when we round it off. All right. So, of course, then 0 equals F applied, 126, so 100 and 4, 5, 6, 71. And when we move that to the other side, we get an answer of negative 171. And I should put my units in now. Let me erase that. We're talking about forces, so it's newtons, and it's F applied. So that means the F applied is negative 171. What's the negative mean? Well, let's go back to our picture. If we look at the way we drew it, we would expect a negative answer because our F applied right here is pointing to the left, the negative x-axis. Remember, our axis is bent. So that's exactly what we would expect. And so that's basically the difference between flat and on a hill. When you are flat, you have net force equations that look familiar like these. But when you are on a hill, you have to follow this process of resolving the force of gravity. Well, first of all, rotating your axis to match the hill, resolving the force of gravity, and then you get F net equations that look like these. Let me put them over here. There we are, right here. And you can see how the gravity is split up a little bit into two pieces that show up on both. Makes it a little bit different. Of course, don't forget, with a more complicated question, you might have more things to add. You can always have more if there are more forces in the question. Or perhaps you may have a question where there is no friction, which means you won't need a friction force. So you don't have to have all these arrows. You have to remember that F net is adding up all the arrows that are on the picture in the x direction. So you can't memorize this and say this is the answer to every question. You have to remember the nuance of F net and what that means. You have to draw a good picture, and you have to look at the picture and see which arrows you're dealing with. If you have no friction in your question, you won't need a friction arrow. If you have no applied force in your question, sometimes a block is just sliding down a hill because of gravity. No one's pushing it. You don't always have to have an applied force. So you have to be careful. And in all the examples that we do in class, you will see all the different examples and the different nuances and how you can adapt this to different situations. But that's the basic idea of how we deal with things on a hill.